Hello friends, welcome to lecture number 35. In today's class, we'll study about Ampere's circuital law. So before getting into Ampere's circuital law, I will try to take you back to chapter number 1, that is electrostatics. Okay? So if you remember properly, in the chapter of electrostatics, we have studied about Coulomb's law. Okay? Now what this Coulomb's law helps us? This Coulomb's law helps us to find out the force between the two charges, as well as it helps in finding the electric field. Similarly, in this chapter I have told you that is your magnetostatics. In the magnetostatics chapter, whatever job the Coulomb's law used to do in electrostatics, the same job in magnetostatics is done by which law? Biot-Savart law. Using this law, we have already calculated the magnetic field at different points. Okay, Biot-Savart law. Now then comes, after Coulomb's law, we have studied about Gauss law, which is nothing but an application of Coulomb's law only. From Coulomb's law we have derived it. So this is your Gauss law. Now if Coulomb's law was there, we can easily find out the electric field. What was the need for Gauss law? Just to make our life simpler. Okay, this Gauss law also gives us the electric field. Coulomb's law was giving, Gauss law was giving. But Gauss law makes our life easier, because in Gauss law what we assume, we all the time talk about a symmetric electric field. We talk about symmetric electric field. Okay, and here if you remember properly, in chapter number 1 we have talked about Gaussian surface, which was either a sphere or cylinder, whose geometry we already know it. Similarly, here in this chapter, once you have studied about Biot-Savart law, where we can easily find out the magnetic field, there is another law which makes our life much more simpler, and that law is your Ampere's circuital law. Okay, Ampere's circuital law. This also helps us to find out the magnetic field, right? This also helps us to find out the magnetic field. But here what we consider, here also the way we have taken Gaussian surface, where there we have taken a surface, here we will take a loop, and that loop is called Amperian loop, and that loop is also very symmetric. Okay, so I hope it is clear to you that in Gauss law we used to find out the electric field easily. Similarly, Ampere's circuital law helps us to find out the magnetic field easily, and moreover here the magnetic field has to be symmetric. Okay, now what is this law all about? Suppose I have got wires, infinite current carrying wires, which are having the current I1, I2, I3, I4. So let me write here, cross indicates the current is into the plane of the paper. So cross I1, here I have dot I2. Dot means the current is moving above, out of the plane. Okay, then I have another here I3, it is cross, and here I have I1, okay, which is dot. Now it is asking that, suppose I choose a point P here. I choose a point P here. It is asking what is the magnetic field at point P due to all the charges, all the current carrying elements. I1, I2, I3, this is I4. I1, I2, I3, I4. Okay, so we have to find out. So how to proceed about it? Ampere told that taking the point P, draw a closed loop, and here the loop has to be symmetric. So what is the symmetric loop here? What we can consider? It will be all about our circle. Okay, so this is the point P here. Followed. Now if I draw this closed loop, then what about the currents which is enclosing it? You see, I1 and I2 are the two current carrying wires which are enclosed in this loop, closed loop. So according to this law, it tells, according to this law, it tells that integration over the closed surface B dot dl will be equal to mu naught I in. What is I in? That means the current carrying elements which are enclosed inside the closed loop which we have considered. Okay, now this closed loop you have to give a magnetic field direction. You have to give the direction to the magnetic field. Suppose I gave it in this manner. I gave it in this manner. So it is quite obvious from this loop and the direction of the magnetic field that here your I2 will be greater, because you see in the magnetic field direction it is going in anti-clockwise. So call all your fingers of your right hand in the anti-clockwise direction. Where is the thumb pointing it? It is above the plane of the paper. So above the plane of the paper means dot. Therefore I2 will be greater than I1. So to be very specific, in this example which I have told you, your integration b dot dl will be equal to mu naught I2 minus I1. Okay. So this is what you have to write down for using Ampere's circuital law. So in words we can write that the line integral in Gauss law, if you remember, it was surface integral E dot dA, but here it is B dot dl. So line integral of magnetic field around a closed loop is equal to mu naught times the current threading through the loop. Threading the loop means which is inside the loop, closed loop. Okay. Now this closed loop which I have drawn, it has got a name. What is the name of that? It is called an Amperian loop. It is called a Amperian loop. Okay. Now we should read in detail about this Amperian loop and what are the properties of the magnetic field which I have assigned on the loop. Okay. So first point which you should understand about the Amperian loop is the Amperian loop. I am writing AL. AL means Amperian loop is not a real loop. But has a known geometrical shape. Okay. So you have to remember this point. Now there are other points also, that the magnetic field or the loop which you have chosen, how the magnetic field should be. Now what is this dl element which I am talking about in this formula? Suppose I take a very small current carrying element, my dl will be in the direction of the in the magnetic field direction. This will be dl. This is the dl which I have chosen. So the magnetic field, it tells that it should be tangent to the loop. So this is the tangent to the loop, B vector. Suppose I take a dl here, okay, then tangent to the loop will be along this direction, B vector. Okay, so you see here B vector and dl, they are along the same direction. Followed? So in this Amperian loop, your magnetic field, these are the few assumptions which you have to take. Your magnetic field is tangential to the loop, or you can say your magnetic field is non-zero constant. Okay, so now you see here integration b dot dl. Okay, dot product means cos theta will come. So b vector direction and dl direction is same, I have shown you. So theta will be how much? It will be 0 degree. Okay, if it will be 0 degree, cos 0 is 1. So b dot dl will be integration over the closed loop b dl. Okay, and b is constant throughout the loop, so it will come out of the integration. You will have integration dl. Okay, so if you assume b to be tangent, then the left hand side of the Ampere's circuital law will be b will be coming out integration dl. Then the other assumption, if b vector is normal, you can take b vector as normal to the loop. Okay, if it is normal, then theta is 90 degree. If theta is 90 degree, integration b dot dl will be equal to 0. Okay, then the third assumption, it tells that b vector vanishes. That means what? That my b vector is 0 itself. If b vector is 0 itself, then integration over the closed loop b dot dl will be 0. So out of these three assumptions, which one suits us best for a particular problem, that we will be accepting it. Okay, so I hope all of you understood. So my Ampere circuital law is what? Integration over the closed loop B dot dl is equal to mu naught I in. This is my broader sense for Ampere circuital law. Now let us apply this Ampere circuital law and try to find out what will be the magnetic field due to a infinite current carrying wire. Okay, so let us go to the give me the heading. So B vector, I have to find out B vector due to an infinite current carrying wire. Okay, followed. So first I have to draw a infinite current carrying wire. I have to draw. Followed, I have drawn it. In this infinite current carrying wire, my current is in this direction. Followed, then what happened? At point P, suppose I took a point P here. This is my point P. At point P, I have to find out the magnetic field. I can use Biot-Savart's law and I can find out. But let us find out using this Ampere circuital law. See, let us see what happens here. So what we will do? We will do an draw an Amperian loop. So the Amperian loop which I have considered here, it is having a radius. This is having a radius r. It is having a radius r here. Okay, and let me consider the magnetic field is in this direction. Followed, it is quite obvious because my current is up, the magnetic field has to be in the anti-clockwise direction according to right hand thumb rule. Okay, followed. Now what is this? This is my Amperian loop. And where I have to find out your magnetic field? I have to find out the magnetic field at which position? I have to find out at this position. Okay, at point P, suppose I have to find out the magnetic field. Followed. So now using your Ampere circuital law, what does it tell? It tells integration over the closed loop B dot dl is equal to mu naught I. Okay, I because only I is the current which is entering. So integration B dl cos theta. So the we know according to the we have chosen the Amperian loop in such a manner that the magnetic field and the dl are in the same direction. So theta will be 0 degree. So here theta will be 0 degree. If theta will be 0 degree, cos 0 degree will be 1. Okay, so this is mu naught I, and I have told you the magnetic field is constant throughout the Amperian loop. So B can come out of the integration. Integration dl is equal to mu naught I. Okay, now dl means it will be your circumference of the circle. So B into 2 pi r is equal to mu naught I. So what is B? B will be equal to mu naught I divided by 2 pi r. So it is quite obvious, you have already seen this expression. By using Biot-Savart law, you have calculated for a semi-infinite wire, if you remember, for infinite wire it will be mu naught I by 2 pi r. Followed. Now after this, let us go for two more applications of your Ampere circuital law. First we will apply it for a hollow infinite wire. So we will apply this Ampere circuital law for a hollow infinite wire. Okay, now how this wire looks like? It is something like this. I am drawing it. Followed. These are infinite, so I am drawing it infinite. Now what I will do is, if I look from the up, if I look at this hollow infinite wire, how it will look like? It will look like a circle like this. It will look like a circle which is having a radius capital R. Okay, so let me draw a line which is exactly crossing at the middle of this hollow infinite wire, so that I can show which one is R. Okay, so this is the aerial view which I am drawing. Followed. So this is it. Now what happens? How the current is going to be in this? If you look at from the top, the hollow infinite wire, you will see the current will be on the surface itself. Inside it is hollow. I am putting cross means the current is entering. Followed. It is just simply entering. I amount of current is entering. Clear? So we have to find out what will be the magnetic field. Clear? So first what we do, we will take a Gaussian, we will take an Amperian loop of radius small r. Let me take it here. Right? This radius is small r. Now I will divide this into 4 regions. Okay? What are the regions? You see here, for r, small r less than r, in this region, that means inside the infinite wire, I will apply Ampere circuital law. Integration b dot dl is equal to mu naught I in. Okay, so this already we have taken the Gaussian surface. B dot dl means b dl cos theta, theta is equal to 0 degree. So you have b will be the constant which will coming out of the integration. Integration dl will be 2 pi r. I am writing directly, which we have already done in the previous case. Mu naught. And what is the current enclosed inside the hollow infinite wire? Inside there is no current. So I in will be 0. Then this implies what will be the value of B? It is 0. So the magnetic field is going to be 0 inside a hollow infinite wire. Now what the other region for R greater than capital R, outside the hollow infinite wire, in this region what happens? Again I will apply Ampere circuital law. B dot dl is equals to mu naught I in. Okay, now what will be in this case? Again this side B into 2 pi r, all of you know it. This will be equal to mu naught, and what is the current? I. Okay, so B will be how much? Mu naught I divided by 2 pi r. So from this we can know that my B is inversely proportional to 1 by r. So now let us plot a graph. Okay, so I will draw my x-axis and y-axis. I will draw a graph for this. Followed, this is my small r, radius of the Amperian loop, and this is the magnetic field. Okay, now what we have seen, we'll see here that the value of B is going to be 0. From the beginning it will be 0. Up to how much? Up to the edges of the hollow infinite wire, where my small r is equal to capital R. Now at that after that what happens? The value of B increases, okay, to a value, and then after that it decays. Okay, it will decay. So here it is inversely proportional to R. So this is the graph for a hollow infinite wire. Now things are going to be totally different when we consider a solid infinite wire. Solid infinite wire. When we consider a solid infinite wire. So let us first try to see, if I am going to take a look from the top view, if I do a top view, how it is going to look like. So it will be a sphere, like a circle like this, having radius r. Now here what will happen to the magnetic field? The magnetic field is the current here will be is into the plane of the paper, and you see the current is available throughout, inside also, inside the wire also the current is there. Okay, the top view will be in this manner. Now let us draw the solid infinite wire. For that, exactly the same way I have to draw, right? A broader one. Then inside this will be extended because it is infinite wire. So I give dotted lines, right? In this fashion. At the center I give the dotted line from which I can calculate the radius. Okay. And what is which one is your R? This one will be your R, capital R. Followed. Now here what is the current which is entering in the wire? The wire, the current is I. Now in solid infinite wire we have to consider a quantity which is called current density, denoted by J. J is your current density. Okay. Now what is this current density? Current density we know it is current per unit area, pi r square. That is your current density. Followed, here also we will take a Amperian loop. Let me consider an Amperian loop here of radius small r. Here also I will have two regions for r less than capital R. That means inside the solid infinite wire. Okay. So what happens here? Again I will apply Ampere's circuital law. B dot dl is equals to mu naught I. Okay. This side, the left hand side we already know theta will be 0 degree, B is constant, will come out, B into 2 pi R will be equal to mu naught, and from this relation what is the value of I? Here it is small I. What is the relation? I will be J into pi R square. Okay, so what will be the expression for B? B will be equal to your mu naught, pi gets cancelled out, mu naught J R square divided by, okay, now here it is capital R square, but here I will not put capital because I am taking which area of the Amperian loop, so it will be small r square. So r gets cancelled out, so you will have here only small r divided by 2. Okay, so this is one of the expression. Followed. Now I can also try to change if I am going to consider which one. We will be considering the expression for, okay, let us keep it in this form only. Let us keep it in this form. I will not change it. Then what happens for r greater than r, small r greater than capital R? Here also again same principle, integration b dot dl is equals to mu naught I. The left hand side you already know, it will be b into 2 pi r. Okay, mu naught, right, mu naught into I will be the current only, so mu naught I, and then b will be how much? Mu naught I divided by 2 pi r. So if you compare these two expressions, here in this region your b is directly proportional to r, and here b is inversely proportional to r. These are the two regions. So let us now plot a graph. I will now plot a graph between my b and r. So this is my small r, this is my b. So I hope all of you could differentiate between small r and capital R. Capital R is the radius of the wire, but small r is the radius of the Amperian loop which we are going to which we have chosen. Okay, so now what will happen? Again I can divide it into two regions. This line represents what? Your small r is equal to capital R, that is the edge of the solid infinite wire. So before, inside what happens? It will increase linearly in this fashion. After that it will be decaying in this fashion. Here it is proportional to r, here it is proportional to 1 by r. Okay, so this is the graph. So this is it for today's class. I hope you all must have enjoyed it. Please do not forget to subscribe my channel. Any queries you have, you can mail me in the mail ID which is given below. Thank you for your kind patience.